Hello again. I'd like to show the AP Physics C students how to derive the law of conservation of energy using calculus. So let's say that we have a ball, and this is for the special case of a ball falling in a vacuum, no air resistance. The only force acting on it is gravity. Okay. So let's say we have this ball falling, and we know, according to Newton's second law, that the net force is equal to ma, right? And from that, we also know that the only force is due to gravity, so that, and let's define down as negative, so we can say then that the weight, or the gravitational force, is pulling it down. And the weight is mg, but since down is negative, that'd be m times a negative g. And so we'll set that equal to ma. But remember that ma can be also expressed as m dv dt, the time rate of change of velocity. Okay? So what we have then is we have that negative mg equals m dv dt. So there's a differential equation. Alright, so I'll just put that as 1. You remember the chain rule? Well, we can rewrite dv dt. Instead of that, we can write it using a chain rule as dv dy, so that's in terms of position, not time, times dy dt. Okay, and remember dy dt is just the velocity. dv dy is now in terms of position instead of in terms of time. So this gives us that dv dt is equal to what? V, this is V here, times dv dy. So V times dv dy. Alright, so we have that result right there. Now if we combine the two, what do we get? We get negative mg equals m dv dt, but dv dt, as we found out, according to the chain rule, can be written as v times dv dy. So I'll just substitute this in for dv dt. Okay, so we end up with m times v dv dy. Alright. We can rearrange this, and I'll just put the v's over on the left and the g's over on the right. We'll just switch it around, and so we have mv dv dy equals negative mg, and we can bring that dy over to the other side. We'll end up with mv dv equals negative mg dy. So far so good. The next step, so we can take this now and we can integrate both sides. So we can integrate both sides. So we'll take the integral of mv dv from, let's say, our initial velocity v1 to our final velocity v2, for our limits. And then we can also, if we take the integral of that side, we also have to take the integral of the other side. So that'd be the integral of negative mg dy from position 1 to position 2. So those are our limits there. All right. Let me get another piece of paper. So now what happens? Well, now we'll just integrate. So that would be, this is to the first power already, right? V to the first power. So we add 1 to the exponent. That becomes v squared. And then we'll have to divide by 2. So it'd be mv squared over 2. And our limits of integration would be from v1 to v2 there. We'll set that equal to the other. Now, dy, if we integrate dy, that just becomes y. So we end up with negative mgy, and our limits of integration would be from y1 to y2. All right. Now let's go ahead and from that we'll evaluate, and we end up with this over 2 is the same as 1/2, so 1/2 mv2 squared, and I'm just substitute v2 in for that, minus 1/2 mv1 squared, and that's equal to the negative of mg y2 minus mg y1. If we rearrange this, we end up with 1/2 mv2 squared plus, and I'll put the mgy2 over on that side also, plus mgy2 equals 1/2 mv1 squared plus mgy1. And this is a very famous law of nature called the law of conservation of mechanical energy. This term right here is the kinetic energy, or energy of motion, and this right here is gravitational potential energy. And the same holds for the other side too. What this means is, let's take an example of a ball on the end of a string. Oops. If we have a ball on the end of the string and we move it up to, let's say, this height here, we'll call it height y2, and here's our baseline height. Okay, and it has a mass of m. Okay, let's say that or let's call this 1 here, y1. Okay, let's say the velocity at this point is 10 meters per second. We'll call that v1. We could plug that into this equation up here and predict what the velocity would be once the ball swings down to any point. We could find the velocity here, 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 or wherever. So if we wanted to call this position 1, this would be y1 here and the velocity v1. But let's say we wanted to find out what the velocity would be here. We'd call the velocity v2. And if we knew the height at that point above our baseline, we could use this equation here to figure out the unknown, either the unknown height, the unknown velocity, or whatever. So anyway, thank you everybody.